Okay. So, good morning, students. I hope I'm audible to you. So, am I audible? And can you see the screen clearly? If yes, please say yes in the comment box. So, am I audible to you? All of you, please respond. Okay, so Deepak, I hope it's audible to you. So see here, we'll see open system analysis. So if you recall past two chapters in introduction of thermodynamics, basically we dealt with systems and their types basically, and different types of boundaries that we discussed. And there in types of systems, we classified systems as open systems and closed systems. And isolated system is one special case of closed system where even energy interactions are not permitted. Correct? This is what we have seen. Then we talked about boundaries and different kinds of boundaries like real, fixed, movable, imaginary, all these kinds of things. So if you see, and then later we talked with something about thermodynamic equilibrium. I mean, we didn't talk about thermodynamic equilibrium, but we talked about thermal equilibrium. So by defining what is thermal equilibrium, we defined what is zeroth law of thermodynamics, and we learned about how this zeroth law of thermodynamics made an impact in the wing of thermodynamics, basically the concept of thermometry. So then we have seen different temperature scales. And after that, when coming into the concept of heat and work, we have seen that both heat and work are transient functions, and both are path functions, both are inexact differentials. All these things we have dealt, and we have defined something called first law of thermodynamics for closed systems. Basically, when there is only internal energy is the energy that is contained by the system, then we define all these things. Correct? So basically, if you remember, for energy of a system, if you would see, we define something called internal energy, which constitutes of all the microscopic energy that is within the system, plus kinetic energy, plus potential energy. These three are the major kinds of energies that are interacting with a system. Correct? So now we'll start our definition from that particular point. So basically, open system. What is an open system? If you recall quickly, open system, a region in space which is under study and where mass and energy interactions are allowed. Mass and energy interactions are allowed. Correct? So this is what we told you. So in second chapter, we have already seen energy analysis of closed systems. Means for a closed system, if you supply some work, then what are different processes that can take place, and what are the formulas for work interactions, then heat interactions. We have seen all these things, and we have seen some good points, and we have seen solved few previous gate problems, nearly some 20 gate problems in yesterday's and day before yesterday's class. Okay, so in today we'll discuss this open system analysis. So if you take any system in general, if this is your system, then you have some boundary. Correct? And how does the boundary look like? Something like this, that separates system with its surroundings. So this is boundary, and everything external to the boundary you call that as surroundings. Correct? So see here. Now, in this open system, we can see both mass interactions can happen, and also energy interactions can also take place. Correct? So we can also talk about energy interactions. So see here. So we'll see how we focus on macroscopic energies now. So if you recall quickly that the topic I discussed about energy of a system is basically consisted of two parts, which is macroscopic and microscopic. Correct? So if you recall a bit, this microscopic energies will it is buffering in the middle. No, I hope it's okay for. Yes, the video is clear. So I hope, Mohan, you have some issue with your net connection. So please check that. So microscopic energy, if you see, we came into some conclusion called internal energy, correct? Whereas macroscopic energy, we came into the conclusion Ke plus Pe, basically kinetic energies and potential energies, means if they have as a whole, correct? So I told you one diagram, if you remember. For example, if this is a system which is having some mass in this, then let us suppose there is some gas here, some fluid. Basically it can be gas or liquid, doesn't matter. Basically you have some fluid. Okay, so if you see, let us try to put a wheel here, so that, or a water generally which has some, something like this. So if you see, this random motion of molecules doesn't produce any useful work, correct? This is v bar. For example, if the direction of this particle is in this direction, then there could be some particle here which is having velocity in this direction, so the effect gets counter balanced. So there is no useful work that is produced by random motion, but basically this unorganized motion of the system. But now if you organize this motion, which is actually, unorganized inside the system, if you can organize this by passing it to a proper channel, then see what happens. Let us suppose the fluid is coming this way. Now if you put a wheel here, let us suppose this is mounted on a shaft, so let us suppose there is some wheel here now. Okay, something like this. Now this fluid which is moving here is capable of doing some work, correct? Means we are converting unorganized motion into organized motion of particles. Organized motion of particles. Since when we are talking about energy, we talk about useful energy in general. So if you see here, there is no useful energy, so we can't tell the kinetic energy of the system is this much, because if you see, the velocity directions are different and the velocity magnitudes are also different in this case. But when you are channelizing this flow to some useful organized motion of particles, then what happens? Every particle within the system has a unique direction. Every particle in the system has a unique direction for velocity, and they have constant magnitude, because continuity equation has to be satisfied, correct? So which means here we can say the system has some kinetic energy which is v square by 2 for every molecule, correct? But here in this case, since this is random motion, we can't define a property as a whole of the system. So if fluid is entering at a particular channelization, then we can say this unorganized microscopic motion of the system gets converted to organized macroscopic motion of the system, correct? So we discussed this when we are dealing with energy of the systems, correct? Did you all remember this concept? I have drawn the same diagram there. So if you remember, we have already discussed this, correct? So if you see, if you see, the unorganized motion of the particles of the system has been converted to organized motion. So where you can tell this has some kinetic energy, because you can see the macroscopic movement of the fluid, correct? So this is what we have discussed in the basic of the second chapter. Do you all remember this much? All of you, I want all of you to respond. So did you all remember this? Yes, Arvind, you didn't come for yesterday's class, I observe. Okay, so see here. So if you remember this, now let us go for an open system analysis. Now let me try to draw an open system here. Okay, so let us suppose there is some input for the system, and let us suppose there is some outlet for the system as well. Let us suppose, let us deal with a simple case, single inlet and single outlet case. Okay, so now let us suppose this is control volume. This is the volume that you are interested in, because you generally want to know what is happening inside the boiler or turbine, such kind of things, correct? So in open system devices, let us suppose this is the control volume. So if you see, there can some mass that can come in, and there can be some mass that can go out. Similarly, energies can also transfer in and out because of different paddle wheel works or whatever the work interactions that are involved. So let me write the things carefully first. let us suppose there is some mass inlet, but generally you'll have steady flow devices, means basically your process keeps on repeating, means devices they generally work on cycles, means the mass flow and mass exit, means basically the mass flow, the mass inlet and the mass outlet are continuous, correct? It's not like you'll run your boiler for just 30 minutes and you'll stop it, correct? They continuously work on cycles, means there is continuous flow of mass into the device and continuous flow of mass out of the device. So if this is the case, let us talk about rates. M dot in means the quantity of mass that is flowing per unit time. Okay. Similarly, let us suppose this is M dot out. Now, let us suppose if some mass is going in and if some mass is coming out in a given time, and suppose if these two are not equal, then definitely some mass will get stored inside this, correct? Let us suppose this is mass of control volume, and d by dt means rate of this mass of control volume will change if these two are not equal, correct? Suppose 10 kg is going in and only 8 kg is coming out, then 2 kg of mass for every given time gets stored inside the control volume. So there is some change in mass of the control volume with respect to time. Okay, so let us suppose mcv is mass of the system inside the control volume. Inside the control volume. Okay, next. Let ECV is the energy of the control volume. Is the energy of the control volume. Okay, so let us suppose some energy is also going in, E dot in, and some energy is also coming out, E dot out. Of course, there is no compulsion that this energy should come out only through this. There can be some heat loss from this system and some heat can go out at mean path. Okay, the energy for leaving the system need not wait till this moment. As soon as it starts coming in from at any of the point in the system, the energy can go out. Okay, so now if you write conservation equations, see, first of all, mass balance. If you write mass balance, the mass that is going in the rate minus the mass that is coming out should be equal to rate of change in the mass of the control volume, correct? Yes or no? Basically, you have, if you don't have these dots, yeah, for a closed system, mass in minus mass out is equal to mcv. But of course, in a closed system, there is no mass interactions. But generally, I'm talking with complete mass. If mass in minus mass out is equal to change in mass of the control volume, then definitely what happens? If you take rates, you can differentiate this equation on both sides with respect to time. That will give you mass flow rate into the system minus mass flow rate out of the system is equal to change in mass of the control volume. Correct? Next, if you write energy conservation equations, energy in minus energy out in rates form is equal to d by dt of energy of control volume. Let us suppose energy of control volume is changing at a rate this d by dt. Okay, so these are two conservation equations, correct? Did you all understand how did I formulate these two equations? Basically, this first equation is the conservation of mass and second equation is the conservation of energy, correct? Did you all understand how did I write these two equations? So these two are governing equations for the control volume analysis. So let us work out the things from here, from these two equations. Is it clear to all of you? Can I go ahead? Okay, so see here. Now, if you have a control volume which is having some inlet like this and of course some outlet like, inlet basically. So now, okay, so this is inlet and that is outlet. So let us plot the boundary. So if you see, this is the boundary for this. Okay, so now see here. What are different kinds of energies that can go into the control volume. Let us see. Let us suppose some fluid is going inside here. So let us suppose there is some fluid block that is going inside the control volume, and there is some fluid block that is coming out of this control volume. Definitely, because when there is some mass flow and there is when some mass outlet, some new mass should go in at every time, and some mass that is already in the control system should come out. Okay. So if this happens, see what's the answers? What's the analysis that we have? Energy possessed by fluid entering a control volume. Entering a control volume. So if you talk about these things, look. We know, since generally for open system devices, we have the flow to be channelized, because here every molecule should travel in this particular direction. So see, suppose if this fluid block is assumed to go inside the block, then every point on this block should move in this particular direction. Correct? So which means there is some macroscopic kinetic energy for the molecules of the system. That is, molecules of the fluid that's trying to enter the system. Correct? Because if this fluid block has to move inside, then this fluid block, if you are treating this as a solid, for the analysis, because you need this block to move inside, then every particle has its direction fixed in a particular direction. So we have some kinetic energy, V square by 2. Now let us suppose this is the reference, ground reference. Then definitely this inlet will be at some height Z1 from this reference. So because of this height, since this has some mass, it has some potential energy Z. And internal energy, because of temperature, is always lying within the mass, within a given mass. So basically, if you see, we have energy is equal to, okay, let me write in smaller terms. So specific energy. So let me write specific energy. So E is equal to, first of all, you will be having some internal energy for this function, for this mass. So U plus, now every particle has a fixed direction. So we have some macroscopic motion of the fluid now. So V square by 2 plus Zz. Correct? Now, along with this, there is one more important energy that this fluid carries. See, this is known to you. Internal energy plus macroscopic kinetic energy plus potential energy. So these two are macroscopic energies, and this U corresponds to the internal energy that is within the system. So if you see, all these three are present. So along with this three, there is one more type of energy that is present. See here. Now, we'll define what is that. Let us suppose there is one adjacent fluid block that is lying here. Okay, one adjacent fluid block that is lying here. Now, for the flow to be continuous, tell me what should happen. This green colored block which I have down here should push this block inside this volume, yes or no? Okay? For the flow to be continuous, this block which is in green colored should push this white colored block into the control volume. So to push that, what it should do, see, suppose if there is some body here. Okay, let me enlarge this particular part. So let us see what's happening. Let us suppose this is the inlet of this control volume, and you have some white block sitting here of fluid. Okay, now the green block which is here should exert some force on this white block in order to move this into the control volume. Correct? This green block should push this white block into the control volume. Now let us suppose P is the pressure at this given instant of this fluid, and let us suppose this length is L. Then this goes into the control volume if this edge comes here. Correct? Means if this edge with this block which is here, if it comes like this, then it's capable of going into the control volume. So the fluid element which is just beside this is pushing. Like if you're standing in a line and if you're pushing the front person, then definitely the line moves forward. Correct? So in a similar way, if you see, this block is applying a pressure P on this particular block to push this inside the control volume. So if you see, if this cross-sectional area is A, area is equal to A, means basically you have this, for this inlet you have some cross section, so P A into L. Now this is similar to something like work done in pushing this block. So if you see, work done is equal to P into A into L, correct? Because this P into A will give you total force that is acting, and L is the displacement that is displaced by the block. So P into A into L will give you the actual values. But now this area of cross section and length are arbitrary because we can take any two. So we'll write this in terms of volume, PV, where V is generally denoted with mass. So we can write specific work is equal to P into V, because this capital V is an extensive property and it depends upon your mass flow rate that is happening inside. But now if you see, this specific work is a property of the system, I mean this specific volume is a property of the system. So P into V will give you specific work done by this green block to push this white block into the control volume, correct? And this work which you are getting as PV is called flow work. And what is this flow work? If you define this, flow work is the flow work of, some books write this as flow energy, is the work done by the fluid, to maintain its own flow. See, suppose if there is no force that is pushing here, then what happens? This flow gets stopped, correct? So there should be some continuous effect so that this motion keeps on going. Similarly here. So which means for the flow to continue, the fluid should do some work on the preceding blocks to continuously maintain this flow, and that work is given by this P into specific volume. Of course, this is specific, means for unit mass flow rate, correct? For unit mass flow, since I'm not talking about power, we are talking about work. So this is for unit mass flow. So now if you see, this block, green color block, is doing some work on this white block to put this into the control volume, correct? So if this block is doing some work on this preceding block, then the work done by this block is stored as some energy in this, correct? See, generally, if I am doing some work and pushing this cap from this particular end position of the board to the top position of the board, then the work I am doing in bringing this particle here is stored as potential energy in this block, in this cap, correct? Similarly, when this body is doing some work on this white colored body, definitely the work that is done is stored as some energy in this body. So which means the fluid particle that is entering inside has some internal energy because of some mass, some kinetic energy because of some organized motion, some potential energy because of this datum difference, and along with these three quantities which you actually have here, along with these three quantities, you have one more quantity which is called flow work, correct? And this flow work is not present in closed systems, because in closed systems there is no mass transactions that are taking place, correct? But only in open systems you can get the total energy that is possessed by the particle is the three common terms that are known to you, plus this flow work, which is the work done by the fluid to maintain its own flow, correct? Which is basically this. So did you all understand clearly why the energy of a flowing fluid is equal to internal energy plus kinetic energy plus Gz plus PV per unit mass? Did you all understand why this PV term is coming here? Are you all okay with this? If you're okay with this, we'll go for the next part. Yes? Clear to all of you? Okay. So which means along with these three, basic kinds of energies, we have some flow work done on the system which is stored as some energy. So let us start our analysis from this particular point. So see here. Let me draw now. So this is my boundary this time. Okay, so if this is boundary, see, there is some mass inflow, m dot in, minus there is some mass outflow, and m dot cv. Okay, let us remove that dot there. So mcv and ecv are energy of the control volume and control mass at any time. Okay, so see here. So if you look for conservation energy equations, if you look at the energy conservation equations that we derived at this point, so mass flow rate in minus mass flow rate out is equal to change in mass of the control volume, and energy flow in minus energy flow out is equal to energy change in control volume. So if you see here, let us write the equations. Conservation equations. Conservation equations is m dot in minus m dot out. Since we are dealing with weights, this should be equal to change in mass of control volume per unit time. Correct? Similarly, energy rate of inflow minus energy outflow rate should be equal to change in the energy content of the control volume. Correct? These are two basic equations. Now see. Now let us see something called steady state. Okay, till now we have dealt for open system analysis, which can be steady or unsteady. Means I never told you this mass flow rate in should be equal to this mass flow rate out. I have never told you this till this moment. Correct? But standardly, if you see all the industrial applications of open systems, they operate in steady state, because let us suppose you have a turbine, for example. Okay. Let us suppose you have a turbine. Okay. So now let's see what happens. Let us suppose every time some quantity of steam is coming in and some quantity of steam is going out. Now let us suppose these two are not equal. Means, for example, let us suppose if this is some 10 kg and only this is some 8 kg, then what happens? After some finite number of cycles, in every cycle 2 kgs of mass is getting stored inside. Correct? So, and you know, volume of this turbine is finite. So after some finite number of cycles, this turbine gets blocked. Correct? Because it is completely filled with mass and there is no permission for the new mass to come inside. So generally all steady flow energy devices, they operate on steady state for mass, because they don't need mass accumulation inside. Similarly, there can't be outlet can't be more than inlet, because if that's the case, power automatically starts decreasing, and after some finite cycles there won't be any mass that is left within. Means whatever is coming in, it will come out very soon without having any work interactions. Okay? So that's why in all practical applications work under steady state, which means this dm for steady state, d by dt of mcv means what is steadiness? Your property should not change with respect to time, so this will be equal to 0. Similarly, for steady state, what about energy content? This energy content should also be equal to 0. Means rate of change of energy content should also be equal to 0, because see, this all materials that we have, all appliances that we have, like turbines, compressors, every material, they have certain temperature limits. Correct? Now what happens if energy keep on storing inside for every cycle? Means if energy inlet, let me write here, E dot in and E dot out, if these two are not equal, let us suppose E dot in is somewhat higher than E dot out, then what happens? In every cycle some part of energy gets stored inside this device. Correct? If energy is getting stored inside the device, then what happens to the temperature of the system? It obviously increases. So if it's keep on increasing, then this material will fail at one particular condition. Correct? Because these materials have maximum temperature limits. So that's why to maintain these two conditions, like to provide continuous inflow and outflow, and to maintain safe conditions within the devices, we will design devices such that this mass flow rate which is going inside should be equal to mass flow rate which is going outside, which means if these two are same, then this value is 0, because on the right hand side we have inflow mass flow rate is same as outflow mass flow rate. Similarly, energy, if you take about energy at steady state, whatever energy is coming in, that should go out. So if these two quantities are equal, then this value is 0. So d by dt of energy of control volume is 0. So that's why for steady state we attain these two equations. Okay, this is unsteady, this device, because if you see 10 kg is coming and only 8 kg is going out. So this is unsteady. So generally for steady state, you have d by dt of mcv should be 0 and d by dt of ecv should also be 0. Clear why these two should be 0 for attaining steady state devices? Yes, see, means whatever you're telling, whatever energy is coming in, that is going out. See, I told you clearly, energy need not go out to mass only. There can be some energy heat interactions, some work interactions that can take place, all these things. Correct? So I told you the total energy out means total from this outside this boundary. It's not only from this particular outlet. I hope I'm clear till now. Are you all understanding this? Vijay Sai, I hope I'm clear now. Heat loss means energy loss is need not be only through this outlet. It can be from any of this boundary. Okay, clear to all of you? So can I go ahead? I want all of you to answer. Can I go ahead now? Okay. So now if you see, we'll talk about steady state devices. Steady state devices. So see here. First, a device to operate at steady state. For a device to operate at steady state, m dot in should be equal to m dot out. Correct? Next, energy dot in should be equal to energy dot out. Correct? So let us enlarge this equation. So this implies m dot in into C. Here we have written specific energy possessed by system per unit mass. Internal energy, see, I have denoted small terms. Of course, velocity, I didn't write mass here. So for velocity and kinetic energies and potential energies, I didn't write mass flows here. And since this V is specific volume, this is per unit mass. So energy per unit mass is given by U in plus P in V in plus V inlet square by 2 plus Z into Z at inlet. Means potentially you can see the case. Means if this is the system, then if you write different terms here, m dot in and energy dot in, and here m dot out, and let us suppose total energy that is going out of the system is E dot out in a given time. Then if this is my boundary, then the energy that is coming in is given by this complete term, correct? Because these are per unit masses, and since we want energy rate, we multiply it with mass inflow rate. So this should be equal to mass out. Okay, so let me write this. So mass out into, see, whatever the work the system is doing here, same, not same quantity, but some amount of work should also be done here to remove this block from this control volume, correct? So whatever the kinds of energies, basically all these 4 kinds of energies that you have here, they will be present here as well. So if you see U out plus P out, V out plus V, this is capital V, which is velocity. So V out square by 2 plus Z Z2. Of course, if they have some datum difference, then this height is Z1 generally, and this is Z2. We have a small height differences as well. So because of that, potential energy comes into picture. Correct? Now, if you go for the recapitulation, what's the basic motto of thermodynamics? To provide some energy input as heat and to get out some work output as energy output. Correct? So if you see, along with energy input, if you add Q, and along with energy output, if you add W, then see what happens. Now, for steady state, m dot in should be equal to m dot out. So let us call this as m dot. Okay, since both are equal, since m dot in and m dot out are same, so let us call this as m dot. So Q plus m dot into U inlet plus P inlet specific volume at inlet plus V inlet square by 2 plus Z times of Z inlet is equal to W plus m dot out into U out plus P out V out plus V out square by 2 plus ZZ out. Correct? Okay. Correct? So see here. So let me write one more step now. This implies Q minus W. Let us put dots here because we are talking about a rate. So Q dot and W dot, because everything dimensionally it should be same. So Q dot and W dot. Let us suppose we are giving some power, some work done within a given time. So Q dot minus W dot is equal to, now see carefully, m dot, because this m dot in and m dot out are same. So I am replacing both the things. This is actually in, m dot in. So since m dot in and m dot out are same for a steady flow device, so I am replacing these two quantities with m dot. So if I replace with m dot, we have U out minus U in. Correct? U out. Okay, let me write these two things, plus P out V out minus U in plus P in V in. This is what you have. Means basically this is change in internal energy plus flow work. I mean basically internal energy plus flow work at out minus change in, internal energy plus flow work at in, plus V out square minus V in square divided by 2 plus Z into Z out minus Z in. Correct? Yes or no? And we got this Q minus W because we are considering that heat is flowing inside and W is flowing outside. Okay, so that's why we have taken a standard sign convention that heat added to the system is positive, so we add it as a plus sign when we are dealing with terms inside, and work coming out is positive, so we are added as positive term when we are treating outside terms. So if I write this equation for one more time in the next page, so see what happens. Q dot minus W dot is equal to m dot into U out plus P out into V out minus U in plus P in V in plus V out square by 2 minus V in square by 2 plus Z into Z out minus Z in. So this is the equation that is with us. Correct? Now tell me, this U plus PV is called, what's the combination of this U plus PV called? We have discussed. Correct? U plus PV is called enthalpy. H is equal to U plus PV, which we gave mCp into T2 minus T1 when we are defining the term constant. Specific heat at constant pressure. So if you see this implies Q dot minus W dot is equal to m dot into, now if you see this U out plus P out V out is same as H out, which is specific enthalpy, minus specific enthalpy at inlet, plus V out square minus V in square divided by 2 plus Z into Z out minus Z in. So this is what we have, and this equation is named as steady flow energy equation because it talks about energy conservation of steady flow devices. So steady flow energy equation, and it's termed as SFWA. Okay, so did you all understand how did we achieve this equation? Clear so far to all of you? Is there any issue at any point? So tell me, is this clear to all of you? I want all of you to respond. So is this clear to all of you? I want your responses. Okay, so we'll see a lot of applications of steady state devices now. What are the applications? Like nozzles, diffusers, turbines, compressors, everything we'll see. But for the time being, did you all understand this equation? So if you understand this equation, I would like to show you something here. See, let us suppose the system is closed now. Okay, if system is closed, tell me one thing, and let us suppose potential energies are neglected, gravitational effects which we have neglected generally. So let us suppose system is closed and potential energies are neglected. Then what about this Z out minus Z in? If potential changes are neglected, Z in is at most same as Z out. So the difference between these two is 0. Correct? So this term gets eliminated. 0. Correct? Next. If the system is closed, will there be any macroscopic kinetic energies for the masses that are coming in and coming out? No. These two terms will also be 0. Correct? Next. In this term U out plus P out V out, this P out V out is the term that is corresponding to potential, flow work of the system. Correct? And flow work is the work done by the fluid to maintain its own flow. But in open system, in closed system, if there is no flow of the fluid, then what happens? This P out V out means the flow works at inlet and outlet are also absent. Then how does this equation look like? Q dot minus W dot is equal to M dot into U out minus U in. So if you see, if you have Q minus W is equal to delta U, then if you divide this with time, then what you will be getting? Q dot minus W dot is equal to du by dt. Means basically energy increase rate, correct? Which can be also directed from this equation. And this, this is first law of thermodynamics that we have, correct? For a closed system. So if you know the analysis for open systems, you can always derive something for closed systems. Okay, so clear. Now we'll see different applications that are involving all this, these devices. So did you all understand how this equation is formulated? If that's fine, then we'll go for the next part. So this is basically the derivation of steady flow energy equation, which is very simple. There is nothing issues in this. So this is the case. So okay, so now shall we go for applications of steady flow devices? I'm going there. Applications of steady flow devices. So now, first application, we'll talk about nozzles. Nozzles. Okay, so nozzle, what's the nozzle? Generally, the device which tries to increase the kinetic energy of the fluid by utilizing some pressure energy, correct? So a device that increases the kinetic energy of the fluid at expense of its pressure energy. Okay, so see here, how does a nozzle look like typically in construction? If you see, it looks something like this. Of course, you'll be seeing some vertical nozzles generally. So this is the case. So what happens? This nozzle, if it's operating at steady state, there will be some mass inflow and there is some mass outflow. So there is some energy inflow and there is some energy outflow as well. Correct? So see here, let us see what happens for a nozzle. So if you see, this is the boundary of this nozzle. Okay, so if this is the boundary, then let us apply the steady flow energy equation, assuming nozzle is operating under steady state. Nozzle is operating under steady state. Okay, so if this is operating under steady state, see what happens. Let us apply the steady flow energy equation. Q dot minus W dot is equal to M dot into delta H plus delta Ke plus delta Pe. Potential energy changes. Correct? Of course, I am denoting small quantities because I need to write these terms with respect to specific terms, because we have a mass multiplied ahead of this. Correct? So now see clearly. Or else if you divide completely with mass, you can also write small q dot minus small w dot is equal to delta H plus delta Ke plus delta Pe. Anything could be fine. So now see carefully. Neglecting q dot comma w dot and delta Pe. Why we are neglecting only these three terms? See here. This explanation is really important. Many times they ask you in interviews. Okay, if for a nozzle, when you are applying steady flow equation for a nozzle, why you are analyzing in this particular way? Look, practically speaking, for a process to be adiabatic, I told you Q is equal to Q dot into time. So for practicality of the adiabatic process, one of these two things can happen. Either this Q dot can be 0, means the heat flow rate is very small, or time should be very slow, means the process is happening very fast. Correct? I told you these two things. Now if you take nozzles, the velocity of gas inside the nozzle is very high. Generally, rocket nozzles and all, they operate at some hundreds of meters per second. Correct? So 11.2 kilometers per second is the speed of the rocket in general. So if you talk about these nozzles, these nozzle speeds are very high at the outlet. And the thing that I want to tell you is, if there is some mass that is entering the system, this mass leaves out the system within no time. Correct? As soon as it goes in, goes out very fastly. Now within this very slow time, there won't be enough time for this mass of the system to interact and to have energy interactions from the system and surroundings, between the system and surroundings. Did you understand? When the mass is traveling very fast, it won't have enough time to exchange heat either to the surroundings or from the surroundings. Did you understand? So that's why in nozzle cases, we assume this Q dot to be very small, 0. And this nozzle is generally not capable of doing any work, because you can't see any work output that's coming out. Only some mass is getting interacted. So there is no some boundary displacement work or such kind of things that are coming here. Correct? So if you see, this work interaction is also 0. Next, neglecting potential energies. This is our assumption actually, because when compared to the energies and kinetic energies that are involved, the height of the rocket nozzle or this change in potential energy is not much concerned with the values when you compare with kinetic energies and enthalpy, because generally at temperatures of 100 kelvins and all, in hundreds of Kelvin, enthalpies will be in hundreds of kilojoules. Okay, so that's why when compared to these two values, the potential energy can be very small and it can be neglected from the analysis point of view. Did you all understand why we are neglecting Q dot, W dot and delta PE from this nozzle? Because this Q dot, this process is happening very fast, so there won't be enough time for the mass to interact with the surroundings and for some heat transfer to take place, either to the surroundings or from the surroundings. Next, this boundary, there is no boundary displacement work or something useful work that is coming out of this nozzle. So that's why we are assuming this W dot to be 0. Next, potential changes, when compared to the values of kinetic energy, where velocity is in hundreds of meters per second, this changes in potential energy is very small when compared. So did you all understand why we are neglecting Q dot, W dot and PE, delta PE? If you say yes, we'll go for the next part. So did you all understand? Yes? Okay. So if you neglect these three things, then see what happens. This m dot, anyhow, if you multiply this here, this m dot gets eliminated. This means delta H plus delta KE is equal to 0. This is the expression that governs the nozzle equations generally. Okay. Clear? So now let us start our analysis from this particular point. Delta H plus delta KE is equal to 0, which means H out minus H in is equal plus V out square minus V in square divided by 2 is equal to 0. Yes or no? So which means if you see V out square minus V in square divided by 2 is equal to H in minus H out. Yes or no? So basically if you see, this value is positive because in a nozzle what happens, velocity, fluid gets accelerated in general. So if this V out is very much more than V in, then what happens, this value is positive. If this value is positive, which means this value is also positive, so H in minus H out, this implies H in minus H out is positive, which implies enthalpy is decreasing. So at the expense of enthalpy, the nozzle accelerates the fluid and increases its kinetic energy. Okay, so there is some enthalpy drop and there is increase in the kinetic energy. Okay, so now if you see some expressions here, V out square, generally in a given nozzle, what happens? Generally, V out will be very much greater than V in. It could be some hundreds of times actually. Okay, so if you take a rocket nozzles and all, this condition is absolutely perfect in that case. Okay, so generally this V out is always greater than V in. So now if you can, this is the case, this means V out square minus V in square is almost equal to V out square, because this V out is very much greater than V in. So if you do the squares, then this value is furthermore very huge. So subtracting this V in square from this V out square couldn't cause a big impact. So if you see this, let us try to put it in this equation. So this implies V out square by 2 is equal to H2 minus, or you can say H in minus H out. So this implies V out is equal to square root of 2 into H inlet minus H outlet. Okay, so this is the expression for the outlet velocity of a nozzle. Clear to all of you? Basically, it's 2 times of inlet minus outlet into 2 under root. Now, if you want this in meters per second, you need to substitute this H inlet in joules per kg. Okay? So let us see that. For a perfect gas flowing through a nozzle, what is a perfect gas? An ideal gas for which specific heats are constant. How these are equal? Okay, I'll let you know. So for a perfect gas flowing through a nozzle, okay, so for a perfect gas flowing through a nozzle, see what happens. H2 or H inlet minus H outlet is equal to Cp into T at inlet minus T at inlet minus T at outlet. Correct? So this implies V out is equal to square root of 2 into Cp into T inlet minus T outlet. Okay. So one of you asked me how to show these units are same. So see here. What are the units of velocity? Meters per second. Correct? For enthalpy, I'm talking about specific enthalpies here. So H is equal to, for H if you see, kilojoule per kg. Correct? Also, if you see joule per kg, because kilo is just a denotation of the quantity. So joule means Newton meter per kg. So this is equal to, Newton means kg meter per second square into meter per kg. So if you see, this kg gets cancelled and you have meter square per second square. And since meter square per second square, since you are putting a square root for the enthalpy term, so square root of this dimension is again meters per second. So that's how dimensionally this equation is also correct. Okay, Vijay, I hope I cleared you. So see here. Okay, is that clear to you, Vijay Sai? So see here. So 2 Cp into T inlet minus T outlet, which means you can see one thing, if the velocity is positive, this outlet temperature is less than the inlet temperature. Okay, so for continuity, but finally, if this initial temperature is given, you can also find out what is the exit temperature of the gas. For continuity, ρ1 A1 V1 is equal to ρ2 A2 V2. These are actually velocities. So ρ1 A1 V1 is equal to ρ2 A2 V2, or you can write in is equal to out, A out and V out. And this density can be written as 1 by specific volume. So A in V in divided by specific volume at inlet is equal to A out V out divided by specific volume at outlet. So if you see, this is also one equation. Sometimes they'll be giving you this thing, out of these 6 quantities, they'll give you 5 quantities and they'll ask you for the 6th quantity. Okay, so generally they'll ask you what's the outlet area of the nozzle, all such kind of questions in gate examination, for which if you have this equation, you could still work out the things. Okay, clear so far? Next, since this process is occurring as per adiabatic process, because there is no heat interaction into this process, we assumed this heat interaction to be 0, this Q dot is 0, you can apply all ideal gas equations to this particular analysis wherever needed. Means PV power gamma is equal to constant, TV power gamma minus 1 is equal to constant, and all these things. So if you know T in, V in and T out, you can get V out generally. Okay, so all these things, it can happen in a good way. So you can calculate area outlet as well. So P naught is equal to rho naught R T naught. So basically, if you know pressure at inlet, you can get temperature at inlet if you know density of the fluid at inlet. So P in is equal to rho at in R into T at inlet. So P at outlet is equal to rho at outlet into R into T at outlet. So you can use all these equations, because all these are indicating, the common relation between temperature, volumes, velocities, and all these things. Correct? So are you all okay with this? So can we go for the next application, diffuser? Okay, so can we go for the next application, diffuser? Okay, so see here. Diffuser, a device that increases the pressure energy, means basically try to increase the enthalpy. Pressure energy of the fluid at the expense of its kinetic energy. At the expense of its kinetic energy. So if you see, it's just a reverse operation of nozzle. So if you see, generally it looks something like this. Okay, these are general diffusers. So they generally try to decelerate a fluid and increase the enthalpy of the fluid. Generally use this when we need to decrease the speed of the moving body. Okay, because there are certain speed limits that are to be followed to put certain objects at certain points. So we'll use these diffusers there. So if you see, analysis is same, because even though it is decreasing the velocity, practical applications these velocities are very high still. So if you see, same equation that we derived for nozzle holds good here. So it is reverse in the operation of nozzle. Reverse in the operation to that of a nozzle. So same equation gets hold here. Delta Ke plus delta H is equal to 0. So this implies V square out minus V square in by 2 is equal to minus H out minus H in, which is H inlet minus H outlet basically. And here V inlet is greater than V outlet, which means H out minus H in is positive, because the main purpose of the diffuser is to decrease the velocity. So if there is some mass flow rate that is going in and energy flow rate that is going in, so you will be getting some mass out, which is same as this, and energy out. And of course, if this is operating in steady state, m dot in should be equal to m dot out, and energy dot in should be equal to energy dot out. Okay, so this is the case. So if these are the cases, then H out minus H in is equal to is positive, which means H out is more, which means the enthalpy increases. Enthalpy increases and kinetic energy decreases. So that's why this device diffuser tries to increase the pressure energy of the fluid at the expense of kinetic energy. So kinetic energy keeps on decreasing and enthalpy goes increasing. Okay, so same equations as for nozzle gets converted. So this minus and plus signs all depends on the magnitudes. So see, in exam, if they give you data for potential changes and all, you need to consider. Okay, see, you should always go for this equation. This is the main heart of this open system analysis, correct? And this is called steady flow energy equation. And if they give some values in exam, even if they give nozzle, and if they give some values, the difference between Z out and Z in, you need to consider that. If they give you some heat is being lost, like 2 kilowatts, 3 kilowatts at maximum, you need to consider that in this analysis. Okay, so if they don't mention anything about heats or potential changes, then you can assume them to be 0. But in general, if they put some values for this Q dot, W dot, and this Z out and Z in, you should still consider them, and you should put in this equation and evaluate out of this two. Okay, means what are the quantity they ask you, basically you need to evaluate that. Okay, so we got something about diffusers. Now let us talk about one important device, which is turbine. So what's the turbine? A device that produces mechanical work output at the expense of enthalpy of the fluid. Means basically your enthalpy decreases and you will be getting some work output at the expense of the enthalpy of the fluid. So if you see a typical geometric diagram of a turbine could look something like this. Okay, so there will be some mass inflow into this turbine and there is some mass outflow out of this turbine, m dot out. And if you go deep into it, you will be having some rotors that are rotating. So generally they will be trying to, this substance when it is acted upon by the blades inside the turbine, it is capable of rotating some shaft and it is providing some useful work. And generally this shaft of the turbine is coupled to the generator shaft in all power plants, and that's why a generator generally when you produce mechanical work it gives out electric energy. So that's how power is produced in power plant. So if you see, this is capable of producing some work. So what they do for practical purpose of this turbines, they will insulate the turbines because they don't want energy to go out. Means whatever the maximum content of energy is available, they'll try to put it inside this control volume, because more the energy you put inside, the more there is possibility for coming off this work as per first law. So if you see, they'll insulate the turbine practically to avoid any unnecessary heat losses. Okay, so next, generally you can't expect heat coming out because the steam is generally at very high temperature. So when compared to surroundings, this temperature is very high, so they don't want the heat to go out, so they put an insulation. Okay, so this is control volume. So if I draw the boundary inside this, let me draw a boundary. Okay, so now if I draw this boundary, see what happens. Definitely there will be some heat interactions that are not possible here because there is some insulation. Work interaction can take place because the main purpose of designing a turbine is to get some work output. Then from here, you'll be getting generally kinetic energies. Suppose if you take the velocity of the fluid that is coming inside and the velocity of the fluid that is going outside, generally they are not much varying, okay, when compared to this megawatts of power that is produced by the turbine in general. Okay, so that's why we generally neglect kinetic energies, because the small differences in the kinetic energies, in the macroscopic kinetic energies of the molecules of the system is very small when compared to the huge power that is produced by the turbine because of the enthalpy, huge value of enthalpy that are present here. Okay, so please take this point. So let us apply this SFW equation. So if you apply the steady flow energy equation, Q dot minus W dot is equal to M dot into delta KE plus delta PE plus delta H. So see what happens now. This Q dot is assumed to be 0 because we are insulating this perfectly. So this is 0 because perfectly insulated turbine. Then when compared to the energies of this work interaction and these enthalpies, this potential energy term and this kinetic energy term can be neglected. Here we are neglecting this because these values are in meters per second and meters, normal joules. So if you see this with enthalpy values which are in kilojoules, these two values are generally negligible for a given turbine. So if you see minus W dot, let us write this W dot as, this minus W dot is the total work output from the turbine. So let us write this as M dot into W dot. Okay, so is equal to, okay, M dot into W is equal to M dot into delta H. So if you cancel out this delta M dot, we have minus W is equal to H out minus H in. And you know, a turbine generally produces work, so work is done by the system. So since this W is positive, this H out minus H in is negative, which means H out is very much less than H in. So this implies, since W is positive, because we are expecting some work out of the control volume by the system inside this control volume, this implies H out minus H in is negative. So this implies enthalpy at inlet is very much better than enthalpy at outlet. So by decreasing the enthalpy of the fluid, this turbine is capable of doing some mechanical work here. So did you all understand why we are neglecting this Q, delta K and delta P? And one caution I forgot to tell you when applying this nozzle equations, this Cp should be in joule per kg Kelvin. Okay, because if you see, this is in meters per second. So to match the units, this H is in, this Cp should be in joules per kilojoule Kelvin. Because to convert this into kg per meter square, you should have joules here on the top. Okay, so when this is in joules per kg, only then you could get these values. So Cp value should be in joules per kg Kelvin. You can add a note here. This Cp in joule per kg Kelvin. Okay, because if you put kilojoules, answer changes because units doesn't agree dimensionally. Correct? So if you see, you should get this. Okay. So did you all understand why for a turbine equation, the work done by the turbine of an isentropic turbine? Okay, we'll talk what is entropy in the next chapter. So, but see, for a perfectly insulated turbine undergoing a reversible process, did you understand why work output of the turbine is equal to H out minus, minus of H out minus H in? So we can say for a perfectly insulated turbine, work output is equal to H out, H in minus H out. After neglecting all those terms. But in exam, if they give you some values corresponding to the potential energies and kinetic energies, you should consider them. Okay. So next, if the gas inside the turbine is perfect gas, then you know, for perfect gas with constant specific heats, this W out is equal to Cp into T in minus T out. So they can give you Cp and T inlet and they can ask you what is T outlet for the process. Okay, since this process is adiabatically controlled because you are not allowing any heat interactions, to apply this T in, T out when pressures and volumes are given, you can apply ideal gas equation all the time. Okay. Cut. Now we'll go for the next device, which is compressors. We'll talk more about compressors in applied thermodynamics course. So we'll define what is a compressor and all these things. So basically in turbine, if you see what happens, pressure drops. Correct? So compressor, a device that increases the enthalpy of the fluid, means basically it increases the pressure energy, means it tries to increase the pressure of a gas. Correct? Compressors are the devices which generally increase the pressures of the gas, that increases the enthalpy of the fluid at the expense of external work input. At the expense of external work input. Okay, so if you typically draw a compressor, could look something like this because generally it compresses the fluid. So if there is some mass flow into the system, and if you are supplying some work into the system, then this mass will go out, and energies are governed by same turbine equations. Okay, because you don't want the hardly end work which is supplied to the system to get lost, so you'll insulate the compressor. So definitely when you insulate the compressor and neglecting kinetic and potential energies, you will be having same expressions which we have in this case for turbine. Okay, so let us write that for a while. So applying SFW steady flow energy equation to the compressor, where you will be mechanically putting in some work, and mass that is flowing inside the compressor is coming out. Let us suppose all these devices that we are discussing are operating at steady states. Okay, so if you see, Q dot minus W dot is equal to M dot into delta H plus delta KE plus delta PE. So if you see, these turbines are generally perfectly insulated. Compressors are perfectly insulated because you don't want the work that you supplied by using some external source with a lot of difficulty to go out of the system as heat. So generally you will insulate the things. So if you insulate, then what happens? This Q dot can go to 0 because of perfect insulation. There is some work transaction that is happening with the system. So neglecting this kinetic energy changes and potential energy changes, here we are neglecting. When you are neglecting this potential energy and kinetic energy changes, so see what happens. This implies minus for unit mass, if you write the terms for unit mass, minus small w dot is equal to delta H. So this implies, since W dot is negative, because we are supplying work onto the system, so since this W dot is negative, this implies you can write since W dot is negative, you can write work supplied to the system. Work supplied to the system. So if you write this, then this implies delta H is positive, which implies H out minus H in is positive. So this implies H out is generally greater than H in, which means the compressor tries to increase the enthalpy of the fluid. Basically, it increases the pressure energy by increasing the pressure by consuming some external work input. Correct? So that's why if you see a device that increases the enthalpy of the fluid at the expense of external work input. So by taking in some work from external sources, from the surroundings, it tries to increase the pressure energy of the system if there is some system here. So again, you can apply all adiabatic laws here, because generally we are not allowing any heat interactions to occur. Correct? So clear to this? If you all are clear with this, we'll go for the next application. And the last application, probably the throttling devices. Okay? Clear to all of you? I want all of you to respond. Okay. So see here. Throttling devices. Basically, what does this term throttling gives you? Passing through a restriction. Passing through a restriction. So basically, physically, if you want to create a throttling process, you can use a pause plug. So generally, in a pipe flow, if you put some pause plug, a pause plug is one which has some perforations to it. So if you take some pause plug and if you put it here, then what happens? The fluid which is coming here so actively will get some restrictions here to pass through, and the fluid experiences some change in its properties. So if you see, this is pause plug. Pause means it has some small holes so that it will allow the fluid, it won't obstruct completely, but it gives some allowance to flow through the body. Okay, so pause plug. In actual practice, this is a restriction. Okay, so this is one physical construction of this throttling devices. But generally, where throttling devices are used, devices that bring down the pressure of the fluid. The pressure of the fluid means basically if you want to refrigerator and all these things, basically you have some valves, throttling valves. So if you see here, generally a throttling valve is denoted by this position, like this is basically the valve that you see that's available for you to rotate in general. So if you look at the inner sense, you will be having, so if you rotate this, the restriction that is available here will get open to some extent. Okay, so this has going, so this height, that the restriction that you allow keeps on changing. So basically these are throttling valves that are applied in practical applications. So you see, in a carburetor made engine, you have a throttling for fuel supply and all these things. So these throttling valves are of much importance actually. Okay, so let us apply the steady flow energy equation for this flow. Which is of course providing some restriction onto the flowing fluid. Okay, so now let us see, this is the control volume where you are choosing this, means just what's happening just and after this throttling. So if you see, if you take this as a control volume, so see here, till here the pressure and velocity and all these things are something which are different from this point. Correct? So if you apply control volume steady flow energy equation analysis for this particular part that I have highlighted here, which is inside the fluid flow, just by throttling this, by rotating this valve, this restriction changes. So this is flow to a restriction. So let us apply steady flow energy equation here. So applying steady flow energy equation, applying steady flow energy equation, we have Q dot minus W dot is equal to M dot into delta KE plus delta PE plus delta H. So if you see here, for small throttling devices, means basically oil pipeline, if the pipeline is of so long length where the fluid motion is almost steady, but you have some throttling wall sitting in between with some very less space. So what happens for small throttling devices, this heat interaction is zero, because as I told you, when the space is very small, the fluid crosses the control volume within very less time. Correct? So within that particular less time, it's really hard for the fluid to exchange heat with the surroundings and from surroundings to the system. So in this, we'll write Q dot is equal to 0 time for the system to cross the control volume is so small. To cross the control volume is so small. So when time is so small, you'll equate this to 0. Similarly, you can see there's no work interactions that are taking place within this fluid and external to this. So W dot is also equal to 0. No work interactions are taking place with effect to this throttling process. Next, if you talk about changes in kinetic and potential energies, when these devices are small, generally there won't be any change in potential energy. And also, when this device is very small, by the time fluid particles really experience some change in velocity, they will already cause the control volume. So you can see this delta K and delta PE are also neglected. So delta KE and delta PE are also neglected. So if all these terms are neglected, see what happens. So this implies Q dot minus W dot is equal to M dot into delta KE plus delta PE plus delta H. So these two are zeros, and this kinetic energy and potential energy are neglected. So this will give you delta H is equal to 0, which means H inlet is equal to H outlet. Of course, this is the case for small throttling devices. For small throttling devices. Okay, so when throttling device is very small, this H inlet is equal to H outlet. Now, for a perfect gas, flowing through the throttling device, for a perfect gas flowing through the throttling device, what could happen? This implies Cp into T inlet is equal to Cp into T outlet. So if you see the Cp is constant for a perfect gas at any condition, so this implies T inlet is equal to T at outlet. Means during throttling of a substance, this implies during throttling of a perfect gas, during throttling of a perfect gas to a small throttling device, to a small throttling device, T at inlet is equal to T at outlet. Means the total temperature change within the process is 0. Okay. So in gate examination, they'll ask you this question. So they'll give you initial temperature and they'll ask you for the final temperature, but generally they are same actually. Okay. So if T are equal, then one thing, given delta H is equal to 0, correct? Because this is what we obtained from the steady flow energy equation analysis. So this implies H inlet is equal to H outlet. So this implies U at inlet plus P inlet V inlet is equal to U at outlet plus P outlet into V outlet. So if you see, if temperatures are same, then this internal energy, which is a point function, is also same. Okay? So which implies this P inlet into V inlet is equal to P outlet into V outlet. But practically what happens? This V outlet will be more than V inlet. Okay? Because fluid suddenly expands at this particular point. So specific volume tries to increase, which means this P out will try to decrease. So that's why generally you experience some pressure drops in the throttling process. Okay. So is that clear to all of you? Did you all understand why I am writing all these things here? Why we are neglecting any quantity at any particular point? So are you all comfortable with all these things? So basically this equation is the main art for all these equations. So if you know this equation and if you know the physical significance of each and every term in this equation, then you can apply this for any given device, after certain assumptions. So clear to all of you? If you are okay with this, then we'll wind up this session today. So tomorrow we don't have a thermodynamics class, and Monday to Friday also we don't have. I mean Monday to Thursday also we don't have any thermodynamics class because I'm off to some place. When we use large throttling device, definitely there is some involvement of kinetic energy changes and things like that. So they'll give you, there is some heat interactions that can take place, Arvind. Okay, so they'll give you the data if something such that is happening. Okay, if they don't give you anything, you can consider H at inlet is equal to H at outlet. Okay, so Sunday means tomorrow we don't have any thermodynamics class. So next thermodynamics class will be only on coming Friday. Okay, at 10 o'clock. So next class is on Friday at 10 o'clock. We'll practice some previous gate problems based on all this open system analysis, and then we'll end up this session. Okay. We are not reducing temperature, Vijay Sai. We are reducing only specific, I mean, we are reducing only pressure. Okay. There won't be any change. That's what I told you, Vijay Sai. T at inlet is same as T at outlet. That's what, you know, the end point of our discussion here. See, T at inlet is same as T at outlet. Clear? I hope, Vijay Sai, that you understood the things. So I hope then everything is fine. This is the open system analysis. So based on this, we'll work out few problems in the coming Friday. Okay. So there is no thermodynamics class till next Friday, 10 a.m. Okay. So we'll see you all at that time. Then thank you all. Take care. If you have any doubts, you can talk to me. See, I'm dealing one more course of basic of engineering mathematics. So in the 9th lecture of basic calculus, I have provided my contact, which many of you are asking for. You can go there. Okay. 9th lecture of basic calculus. Okay.